So this screencast is going to be a very basic intro to kinetics. Nothing in here is there's nothing in here that's not from general chemistry, but you might be a little rusty, so I thought I'd include it. So in kinetics, we talk about how fast a reaction occurs. And so let's imagine we've got some reaction. We've got some molecule A, some other compound B, and maybe they're going to form 2 moles of C. So if we were to graph concentration of those reactants as a function of time, we might find a set of curves look something like this. There's the A curve and B curve. And of course, we're going to be producing some sort of product. So obviously, the slopes of all these lines are different. We have to have some way of writing the rate. And the way we write the rate is to define the rate in terms of those slopes. What we say is that the rate is defined as 1 over nu I, the derivative of the concentration of that component I with respect to t. In other words, this derivative is just the slopes of these lines over here. So remember, nu are these coefficients over here. And just as we did in thermodynamics, nu is going to be positive for products and negative for reactants. So for this, we could say that the rate, which is often given the symbol v as if it's a speed, is going to be not the slope of A, because A has a coefficient of -1 because it is a reactant. So it's negative dA dt would be equal to -1/3 dB dt, and that would be equal to 1/2 dC dt. Now let's say 2 things about this. One, this sort of makes sense, right? This says that the way of saying this is dB dt, we could say, is equal to 3 times dA dt, right? B is going to be eaten up 3 times faster than A, because for every molecule of A the reaction eats up, we're going to eat 3 molecules of B. So that kind of makes sense. Now this set of equalities, it's present in all general chemistry and P-Chem books, but we have to be careful because this last equal sign between products and reactants is not always true. This is only true if there's no stable intermediates between A and B and C. If there's stable intermediates in there, then those intermediates can build up. And if they build up, we can be destroying A and B, but not making C. Okay, so in other words, if we have a reaction pathway that goes A plus B goes to, let's call it G, and then G goes to C, what can happen, especially if this second step is slower than the first step, is that we can have the A curve and the B curve, and all that happens is we make a lot of G. And that G might slowly react. And at that point, we're going to now start forming C. And so we can see that these slopes are related to this slope, but they're totally unrelated to this slope over here because we're building up intermediate. So just be aware that that subtlety is kind of glossed over in most books. Now, the rate of the reaction is usually a function of the concentration of reactants it may be a function of the concentration of products. This is really often true in biochemistry, where we have auto-inhibition of a reaction, where the product of a metabolic pathway will be something that inhibits the enzyme that catalyzes that pathway. So products can also be in a rate equation. The concentration of a catalyst like hydroxide or hydrogen ion can often be in the rate equation. So those are things that affect the reaction rate. And this reaction rate is also going to be a function of temperature. Okay, so how do we write this in some sort of compact notation? What we say is that for many reactions, there's going to be a very simple expression where we have a constant, and the functionality in the concentrations of reactants might be very simple. It might just be something where we have integer, in some cases non-integer exponents here, and then a constant. And we should be a little bit careful here. This constant is not really constant. It's going to be a function of temperature. Not all reactions have this simple expression. Many don't. But it's pretty common that they do. So we often find reactions that are this simple. And if they are this simple, we can say this reaction has alpha order in A and beta order in B, and the overall order is just the sum of those. So the overall order would be alpha plus beta. And so we could say, for instance, just do a quick example, if we had K A B squared, if the rate of our reaction was equal to this, then we can say it's first order in A, second order in B, and third order overall. And just to give you a counterexample of something that wouldn't have an overall order, if you had a reaction that had this expression for the rate, there's no overall order. So imagine something that has this expression for the rate. There's no way to just add up those exponents. It's not a simple product. Now, even in this case, though, we can, under some conditions, say that there's an order. So this one we say, in general, it has no order. But you can see that if you ran this reaction in a condition where the concentration of A was much bigger than the concentration of C, then this term might be negligible. And then we could just have these two terms, and we can actually write it, a simple expression. It's important to note that we cannot get the order of a reaction, we cannot get the rate equation from the overall reaction. We have to have the detailed mechanism. And we'll look at getting reaction orders from detailed mechanisms later. For now, we note that we can't. And so just to give a quick example, if we had T-butyl bromide and we let that react with hydroxide, you know what we can do. We can hydrolyze off the bromide and get T-butyl alcohol and the bromide ion. And looking at this, because of the steric hindrance, we know this is going to be SN1. In other words, it's going to be a first order. We could write the rate as some rate constant times the concentration of T-butyl bromide. On the other hand, if we had this methyl bromide, we did the same reaction, we know that we'd end up getting an SN2 reaction because we don't have any steric hindrance here, and this does not make this makes a pretty bad carbocation, right? So this can come and attack from the back with a simultaneous leaving of the bromide. And so with an SN2 reaction, we know the rate is equal to the rate constant times the concentration of the nucleophile and the concentration of our electrophile. So here we have an overall second order, here we have an overall first order. Notice that the reaction is the same, right? We have a nucleophile plus electrophile, electrophile plus nucleophile. So the overall reaction looks the same, and yet the kinetics are different. And that's because the mechanism is different. The mechanism will always determine the kinetics. So although we can go from mechanism to the kinetics, we can't just look at the overall reaction. To show that it's not always obvious what the rate equation will be just by looking at the overall reaction, let's look at this gas phase reaction where we've got acetaldehyde decomposing to form methane plus carbon monoxide. The rate equation for this does have a simple rate equation. It does have an overall order, but the order is 3/2. And you certainly wouldn't guess that just by looking at the overall reaction. So we actually have to know the mechanism and be able to analyze it to get this. And that's something we'll do later on in this chapter.